All right, today we are diving into one of the absolute beasts of theoretical physics, the Polyakov path integral. Now, this isn't just some dusty equation, it's the mathematical engine that makes string theory go. And as we're about to see, if you follow its logic, it leads to one of the most bizarre and famous predictions in all of science, a hidden truth about the very fabric of our reality.
Okay, so to get where we're going, we need to start with something a little more familiar. You might have heard of Richard Feynman's incredible idea, the path integral. The basic idea in quantum mechanics is this. To find the probability of a particle getting from point A to point B, you don't just find the best path. No, you have to add up every single possible path it could have taken, even the crazy, zigzagging ones.
Now, here's where string theory grabs that idea and just cranks it up to a whole new level. A tiny point particle, as it moves through time, traces out a one-dimensional line. We call that a world line. But a string, well, a string is already a one-dimensional thing. So when it moves through time, it sweeps out a two-dimensional surface, a world sheet. So our path integral is no longer a sum over all possible lines, it's now a sum over all possible surfaces.
So here's the roadmap for our journey today. We're going to look at what these string paths, these world sheets, actually look like. We'll see how their shapes literally encode the interactions between strings. Then we're going to hit a massive problem with infinity, uncover a deep quantum glitch in the math, and see how fixing that glitch forces an unbelievable conclusion on us. And finally, we'll see how it all gets put to work.
Okay, first things first. What do these world sheets actually look like? We need to get a picture in our heads of these fundamental surfaces.
And this picture shows the two basic flavors perfectly. Over on the left, you've got an open string. It's got two ends. As it moves through time, its world sheet is basically a ribbon or a strip. Simple enough. But on the right, you have a closed string, a loop. As it moves, its world sheet becomes a tube or a cylinder. These two shapes are the basic canvases for everything else in string theory.
So we're summing over all these surfaces. But here is where the real magic kicks in. In string theory, you don't have to add interactions to your theory separately. The interactions are baked right into the geometry of the world sheets. The shape of the surface is the interaction. It's incredible.
And this is the classic example, right? The famous pair of pants diagram. What you're looking at is just profound. That single smooth surface shows one closed string, that's the waistband, moving along, and then smoothly splitting into two separate closed strings, the two legs. Splitting, joining, it's all just different ways of looking at the same piece of geometry. No sharp corners, no special points, just smooth fabric.
And of course, it gets way more complex. We're not just summing over these simple shapes, but over every possible shape, or topology. A world sheet with a hole in it, like this donut without the middle shape, represents a quantum fluctuation. You know, a weird temporary event, like two open strings that touch for a moment, form a closed loop, and then break apart again. Every twist, every turn, every hole represents a physical possibility we have to add to the sum.
So, the mission is to add up every single possible shape that a world sheet can take. But if you try to do that, you run smack into a huge mathematical brick wall. You get infinity. The problem is all about redundancy. See, you can stretch or warp the coordinates you're using to describe a surface in an infinite number of ways, but you still end up with the exact same physical shape. So summing over all of them is like trying to count a single photo by counting every possible way the pixels could be arranged to make it. You are just massively overcounting, and your answer blows up.
So how on earth do you fix that? Well, there's a really clever mathematical tool called gauge fixing. Imagine all the different mathematical descriptions for one shape are like a bunch of identical photos in a camera's burst mode. What this procedure does is it defines a slice that just picks out one single representative photo from each burst. It's a way to make sure you only count each unique physical shape exactly once.
It really boils down to a three-step process. First, you figure out what the redundancies or symmetries actually are. Second, you define that slice to pick just one unique version from each group. And third, you do a calculation that effectively divides out all the copies you don't want. And poof, the infinity is gone and you get a nice, finite number to work with. But you know how it goes in physics. You fix one problem and you uncover a much deeper, much weirder one. It turns out that this whole gauge fixing procedure, the thing we absolutely need to make the theory work, it accidentally breaks a really important symmetry of the theory, but only at the quantum level. It's like finding a glitch in the matrix.
This glitch has a name, the Weyl anomaly.
Classically, on paper, string theory has this beautiful property called Weyl invariance. All that means is that the physics shouldn't change if you locally stretch or shrink the world sheet. It's fundamental. But the problem is, the very act of cleaning up those infinities and doing the quantum calculations breaks it. The math suddenly stops respecting this core symmetry.
And as the textbook says right here, a key mathematical term that should be zero in the classical theory, well, it just isn't zero anymore once you do the full quantum calculation. A broken symmetry like this is normally a complete disaster. It means your theory is inconsistent, it's spitting out garbage, it's a sign that something is fundamentally broken.
This could have been the end of the road for string theory. Seriously. But what physicists found next is just one of the most stunning moments in all of science. The theory itself held the key to its own rescue, a very specific condition that had to be met for this quantum glitch to just vanish.
So they sat down and calculated the exact size of this glitch, this anomaly, and they found it was made of two parts pushing against each other. The first part depended on the number of space-time dimensions the string was living in. We'll just call that D. The second part was this weird, unavoidable mathematical artifact from the gauge-fixing trick itself, something physicists call ghosts. And the size of that ghost contribution was always the same number, minus 26.
So for the theory to make any sense, for that quantum glitch to go away, the two parts have to cancel out perfectly. The total has to be zero. So D minus 26 has to equal 0. And there's only one way for that to happen. This isn't a choice, it's a mathematical demand. The only way for string theory to be consistent is if the number of space-time dimensions is exactly 26.
And that's why this is so much more than just a piece of trivia. D equals 26 is the magic number that makes the whole machine actually work. Once you plug that in, you have a consistent theory, and you can finally use the path integral to calculate real things, to make actual predictions about how strings are going to behave.
We can finally calculate stuff. For example, we can figure out the probability of a process like this one, 4 closed strings flying in from far away, interacting in some complicated mess in the middle, and then flying back out. The path integral, summed over all the possible world sheets that look like this, gives us the actual number, the probability.
So how do we tell the path integral what we want to calculate? We use these things called vertex operators. The easiest way to think about them is like little pins you stick onto the world sheet. You put a pin here and you're telling the calculation, okay, an incoming string with this energy and this momentum popped into existence right here. You put other pins for the outgoing strings. They're the things that define the beginning and end points of the interaction we want to measure.
So let's just step back and appreciate the crazy chain of logic we just followed. We took Feynman's sum over paths and leveled it up to a sum over surfaces. We realized the shape of these surfaces is the physics. We hit an infinity, tamed it with a clever trick, but that trick revealed a quantum glitch that almost killed the whole theory. And then we found that the glitch only goes away if, and only if, the universe has 26 space-time dimensions. Wow.
And that, of course, brings us to the elephant in the room. The math is relentless, the logic is tight, but it leads to a conclusion that just seems to fly in the face of everything we experience in our four-dimensional world. If the theory demands 26 dimensions to work, then where are the other 22? And that is a question for another day. Thanks for diving in with me.